Hi everyone, we're Team 2 and we're going to be talking about our apparatus, the Pesti-clean. My name is Samita and I'm a biosystems engineering major.
My name is Tina, and I'm a biomedical engineering major.
My name's Robert, and I'm an electrical engineering major.
And my name's Luke, and I'm an aerospace engineering major.
As you all know, we need water to live, so it's important that everyone has access to clean water. Unfortunately, this isn't the case for the villages in the Makueni County of Kenya, where farmers have been dumping pesticide cans into the River Athi, which is the main source of water for the residents. And as a result, this contaminates the water, which poses as a serious health risk to the residents. So we wanted to create a solution for this.
Our solution will be directed towards the agricultural industry in Kenya. Doing so will allow us to mitigate the source of water pollution, which is pesticide can waste, as Samita mentioned. Next, Robert will talk more about our design solution.
For our design solution, we wanted to be sure that our apparatus is easy to use, safe for our consumers, inexpensive, efficient, and durable. The key features include an LCD display and a water pump. The constraints we had involved the solenoid valve and the amount of water we had in the original design. The water pump replaced these two constraints and eliminated the wasted water. All of this is to ensure our consumers can wash pesticide containers so they can properly be recycled. Now Tina will address the design process.
After research, we found that the lack of government enforcement and general awareness were the biggest factors as to why there are so many pesticide cans in the river. With this, we want to create an accessible apparatus dedicated to collecting the pesticide cans for cleaning and proper disposal. We also found that one of the general and more effective protocols to washing pesticide cans is the pressure rinsing method. This inspired us to include a water jetting mechanism in our device, which is indicated by the tubing and water pump in our graphics. In addition, we created a 3D print of a pesticide can fixture in order to hold the can in place during the washing process. Now that we know our design process, Samita will explain exactly how our prototype works.
So the way our prototype works is, first, the user will place the pesticide can upside down into the pesticide can holder. Then the LCD will prompt the user to press the push button in order to start the wash cycle. Once the user presses the push button, the water pump will pump water into the pesticide can, and then the wastewater will drain through a hole that's connected between the first tank and the wastewater tank. So now that we know how the prototype works, Luke will be talking about our test results.
So while testing, instead of using pesticides, we used diluted soy sauce, which has a similar pH of around 5. For our first test, we kept the wash time constant for the cans, but we varied the initial amount of pollutants in each cycle. And in the second test, we kept the initial amount of pollutants constant, but we varied the wash time for each cycle. Our hypothesis was that longer wash cycles and lower amounts of initial pollutants will result in the cans being cleaned better or having a pH closer to 7. Our results confirm our hypothesis, however, not as strongly as we would have liked. This is likely due to inconsistencies with our nozzle and water pressure. Now, Robert will talk about our future plans.
For our future plans, our team wants to increase the dimensions of the device so we can wash more cans simultaneously. We want to add a sprinkler mechanism to increase the pressure and range of water. And finally, add a function that allows the user to adjust the wash time. Finally, Luke will conclude our presentation.
Thanks for listening to our solution for pesticide can waste in Kenya. If you'd like to follow up with us, you can contact us via email as seen on our poster.